In this lesson, we will be modeling exponential functions. A quick reminder, exponential growth and decay. You can use exponential functions to model the way certain populations increase or decrease over time. Increasing can be modeled by an exponential growth function. In the same way, we can represent depreciation, which is the decline in an item's value. When an item loses about the same percent of its value each year, we can use an exponential function to model the depreciation or decay. What are exponential growth and decay? Exponential growth and decay are rates which represent the change in quantity through some time. Exponential growth and decay is growth in which the rate of growth is proportional to the current size. So we can actually determine growth and decay just by looking at an equation. The most important feature we need to look at, we have a times b to the x. We need to look at b. So as a reminder, if b is greater than 1, we have growth. If b is between 0 and 1, we have decay. So let's go ahead and highlight the b value in this first one. It is 1.45, which is greater than 1. So this function is growing. In the second function, we have 0.8, which is smaller than 1. So we have a decaying function. To determine the percentage of growth versus decay, you will take, for growth, we know that this is growth, you will take your current rate, so 1.45, and subtract 1, which is our base, to get your current rate. 1.45 minus 1 is 0.45. If we want to change that to a percentage, we move our decimal 2 places to the right, so this would be a 45% increase. If you are dealing with a decay, you're actually going to take 1, subtract your rate. So subtract 0.8, which would give you 0.2. If you move that 2 decimal places to the right, you would get 20%. Some real-world situations that we would have here. Let's say a stereo costs $900. That's our initial value A. Its value is decreasing by 12%. So we're going to take our value of 1 and subtract 12%. 12% as a decimal is 0.12. We have our 12%. We're going to move it to the right or to the left twice. 1 minus 0.12 is 0.88. So if we're going to write an exponential function that models that, here is our standard form. We said A, the initial value was 900. It's decreasing by 12%, which is 0.12. So we would take our A value, plug in 900. 1 minus 0.12 gives us our decreasing rate. So this would be our function. 900 times 0.88 to the x. Suppose you buy a computer that costs $2,000. That's our A. And expect it to depreciate. That means it's decreasing by 30%. 30% is the same as 0.3. What will the computer's resale value be in 4 years? Now we're not only writing a function, we're going to evaluate. So y equals A times b to the x. A is 2,000. That looks like 20,000. This should be 2,000. B, to find our rate, we're going to take 1 minus the rate. So 1 minus 0.3, which is how we get this 0.7. And then our x is our years, which is 4. You would just type this into your calculator. So I would do 2,000 $1,000 times 0.7 to the fourth, which would give me $480.20 after 4 years. That's how much my computer would be worth. An insect population of 2 insects increases at the rate of 450% each week. What will the insect population be at 4 weeks? Initial value, what did we start with? We started with 2. A is going to be 2. This one's tricky. It increases at 450%. That's a ton. We're going to move our decimal places 2 places to the left. So we're increasing by 4.5. And we're going to add that to 1. So we're actually going to have a B value of 5.5. We take our initial value, 2, and plug it in. 2 times 5.5, and then our number of weeks is 4. Raise it to the fourth, and we would go from 2 insects to 1,830 in a matter of 4 weeks.